Okay, so now we're going to take a look at one of the subatomic particles, probably the most important subatomic particles that governs or that dictates the behavior of atoms and elements. And those are the electrons, right? So when it comes to the behavior of atoms in general, if we know a little something about the electrons, we can actually predict how things are going to behave. So we can say electrons are the most important subatomic particles, and this is because they will dictate chemical behavior, and we'll see why this is here in a second. So if I have, and we've looked at our model or general sort of overview of what an atom looks like. So at the center of the atom, we have our nucleus. Okay, and in the nucleus, we have our protons, and we have the neutrons. And then orbiting or anywhere outside of the nucleus, we have our electrons. So these electrons, first of all, they're on the outside, right? They're sort of away, they're far away from the nucleus. So if I have another atom, let's say this blue one over here on the right side, nucleus at the center, and then you have your electrons all the way around. If I were to bring these two atoms closer together, okay, so if I wanted them to react, in other words, or to interact with each other, I physically have to bring them close together. And if I bring them close together, guess what? The subatomic particles that will see each other first, or that will interact with each other first, will be these electrons, right? And that's why if we know a little something about the electrons, we can predict what is going to happen. Now, these electrons that are found in an atom, they reside, so the electrons reside in energy levels. We're going to call them that for now. And we're not going to get very deep into electron configuration and the whole physics behind this, which is quantum theory and quantum mechanics. We're just going to take a look at an overview, sort of a broad view, and just give you enough information to understand what we're going to be seeing later on. So these electrons and reside in energy levels around the nucleus. Okay, so you can think of these energy levels as analogous to, sometimes they're called shells. And as another term that you'll see that is not 100% correct, but in terms of just what we're trying to get across here, it works well. So shells or orbits. And the analogy here is sort of like the solar system or a planetary system, where at the center of the solar system, for example, you have the sun. That is kind of like the nucleus, right? So if I were to make the approximation, this here was kind of like the sun, and then orbiting around the sun, you have the planets that orbit in an orbit. Well, those planets are analogous to the electrons, and those orbits are analogous to these shells that are called energy levels. So the key thing about these energy levels or these shells is the following. The further the energy level is, or the shell is from the nucleus, the more energy is associated with it. Okay, and thus, any electrons residing in that shell will have a higher energy as well. So the electrons uh, will have higher energy if they are in an energy level or a shell further away from the nucleus. So for example, if this is my model here for our atom, so we have the nucleus at the center, there's an electron in one shell, and further away I have another orbit or another shell with some one or more electrons there. Well, this electron in orange, let me see if I can get the right color. So this electron here in orange, this one has a higher energy, and I'll use E for energy, than uppercase E, than the electron in an orbit closer to the nucleus. This one is going to have a lower energy. Okay, that's the key thing you want to realize it from this, is that the closer the electron is to the nucleus, the lower the energy it has. The further you get away from the nucleus, the further the orbit, the further the energy level, or the higher the energy level, the higher the energy associated with any electrons that are residing in that orbit or that energy level. Now, we use a term to describe the energy level or the orbit that's furthest away from the nucleus, or the outermost energy level or shell, outermost shell or the outermost energy level. We call that the valence, V-A-L-E-N-C-E, shell. And these valence shell, well, that valence shell, whatever it is for an atom, will contain the valence electrons. Okay, so we mentioned before that when two atoms come close together, when they interact with each other, it's the electrons that see each other first, right? Now, not all of the electrons are important. It's the electrons that are furthest away from the nucleus that are going to see each other first, right? And you think about it, that should make sense intuitively. If this atom here were to come close to another atom, it's the orange electron that will interact with the other atom first. That's the electron that resides in the valence shell. That's the valence electrons, right? So the valence electrons then are the electrons that are most important. So these valence electrons are the ones that will dictate chemical, let's say, properties or characteristics, okay, reactivity, how this behaves, how it reacts with other things, as well as a lot of other features are dictated by those valence electrons, right? So the valence electrons are the outermost electrons, the ones that are furthest away from the nucleus, that are found in the valence shell or the outermost shell or the outermost energy level. So how do we know where or how many electrons are in the valence shell and all that stuff? Well, we can actually go back to the periodic table to help us figure that out. So there's our handy periodic table, same one we've used before. Now, we said that when we look at atoms, right, remember that, so I was going to say recall, when we have an entry in a periodic table like helium, for example, it's the atomic number that tells us the number of protons, okay? And if these are atoms, which they all are to begin with, so for atoms, the number of protons has to equal the number of electrons. Okay, so that means that helium, for example, the helium atom, so the He atom, has 2 electrons. The lithium atom over here, this is going to have 3 electrons. The beryllium atom will have 4 electrons, and so on and so forth. So where are these electrons found? Which shell are they found in? Well, in a typical atom, we have the first shell. We designate that as N equals 1. So N here is the shell or the energy level. And that first shell can hold a maximum of 2 electrons. When we get further away to the second shell, okay, so that's N equals 2. That can hold a maximum of 8 electrons, okay? So, and I'll show you how you can use a periodic table to determine where those electrons are. So let's use an example here. We'll start at the beginning with hydrogen. Okay, so hydrogen up here on the left side, first element on the periodic table, we know that it has one electron, okay, because there's only one electron in it. So for hydrogen, we can say that electron is arranged as simply just one, right? So we write the one electron as just a one there, and that's going to belong in the first energy level or the first shell. For helium, that has two electrons, so this one over here, right? That's going to have two, obviously, and that's going to fill then that first shell with two electrons. When we get to lithium, over here in green, right? So lithium has three electrons. So where are those electrons going to go? Well, lithium, the first two electrons are going to fill that first shell. And then we have one more electron remaining. That's now going to go into the second shell. So we put a dot to separate the first and the second. And then we put the one remaining electron there. If we jump then to the next element, which is beryllium, Be has four electrons. Okay, so Be then would be two, and then dot, there's two electrons remaining, two. We jump across, we have boron, this one here that has five electrons. So boron would be two, fill the first shell, and then three remaining goes in the second shell. And then we have carbon that has six electrons, two fill the first shell, four fill the second. We get to nitrogen that has, how many is that? Seven, right? So we're over here now in this region. Nitrogen has seven. The first two fill the first shell, five go into the second shell. We have oxygen that has eight. So the first two fill the first shell, the six go into the second shell. We get to fluorine that has nine. So two fills the first, seven fills the second, and then we get to neon. Okay, so neon then has a total of 10. So then we get to the two fills the first, and then the eight now completely fills that second shell. And now we go to the third period over here. We'll do this one in green. I'll only do a couple of these just to show you how easy it is. We get to sodium. Sodium has 11. So Na, right? The first two fill the first, the next eight fill the second, and then the third shell is where that remaining electron is going to go. And if I go all the way across, so let's say I jump over to chlorine over on this side, okay, and this is how the periodic table is going to help you. I'm going to go through this slowly with you. So if I wanted to find the electron arrangement for chlorine, so first of all, what I want to do is locate where the chlorine is. It is here. Okay, and I'm going to start at the top left, start with hydrogen. I'm going to work my way across. So to get to chlorine, I have to go through the first period. I have to go through those two elements. That's your first two electrons. So two. Let's do that in purple. So two. Then I get to the second period. So I need to go through how many elements here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that gets me 8 as my next set of electrons. Then to get to chlorine, I have to go into the third row, the third period. And how many elements do I have to get in the third row to get to chlorine? I have 1, 2, 3, 4, 5, 6, and then 7. So 7 to get to chlorine. And then this would be my electron arrangement for Cl, 2, 8, and then 7. Right? So it's, again, we're not going to go too deep into the periodic table because there are some exceptions down the road that we'll see. But I just wanted to go through maybe the first three rows with you, the first three periods, to show you how easy it is to determine these electron arrangements, right? So what we just went through here, right? These are known as just generally as electron arrangements. And when we arrange the electrons this way, what you can notice then is that we have a certain set of electrons that come in at the end, right? The last set of electrons that you put in your arrangement, the ones that I'm highlighting in green here, those are the electrons that belong in the valence shell. Those are your valence electrons. Okay, so the valence electrons are in green. So you can determine how many valence electrons you have okay, by simply coming up with the electron arrangement and then seeing where those final electrons go, how many of them you have. All right, that's essentially what I wanted to cover here with the electrons, where they're found and how they are arranged in a particular atom. Now, again, we're simplifying this a lot. So let me put that caveat out there. It's a lot more complicated than this, but we don't need to get into the weeds a whole lot with this discussion. We just need to determine how many and where those valence electrons are located. And it's a quick way that we can do it using the periodic table.